Okay, so this AP problem deals with a lot of concepts related to electrostatics and magnetism and forces in motion. So it combines a lot of things together, along with some experimental data analysis. All right, so the first thing is that we have a charged plastic sphere that's falling inside parallel metal plates, so basically a capacitor. And there's no air, so it's in a vacuum. So the only force that's acting on the sphere is gravity until we apply a potential difference across the plates, and then we have an electric force too. So our question is, what potential difference must we have such that the sphere falls at a constant speed? So the first thing is to figure out sort of what that conceptually means, right? If this is my sphere, right, then what forces act on it such that it could fall at a constant speed? Well, there's the force of gravity. That's definitely true. And so if that's the only force, it's going to accelerate, right? The net force will be down. The only way to make it fall at a constant speed is if there is an electric force that points up, such that the electric force and the weight are the exact same magnitudes, right? And so this tells us that using Newton's second law, Fe minus Fg equals 0, right? That's the description of the motion and the net force from my diagram. And so now we need to figure out how to express these things in terms of what we're allowed, right? M, L, V, and constants like G, basically, or epsilon naught or K or anything like that. So the first thing you might think that I should use for this, Coulomb's law, right? K, Q1, Q2 over R squared. That is a bad idea because this is not an interaction of point charges. That's not what the electric force is, right? All we know is there is a potential difference. We don't know what causes it. Well, actually, we kind of do. It's the metal plates, but it's definitely not point charges. So Coulomb's law will not work, right? But we know something about the electric potential related to the electric force for a capacitor, right? We know that in capacitor, the electric field equals, well, actually, let me do it this way, right? The electric field times the distance equals the potential, right? And we know in general a relationship between the electric force and the electric field. Right? The charge, test charge Q times the electric field E gives the electric force. So we can put all this together and write that the electric force is QV over, in this case, L. Right? L is the distance, I should probably clarify that, right? L is the distance between plates. Right? So, this expression right here is the electric force felt by a charge Q in a capacitor with potential difference V and size L. So that's good. And we know what the force of gravity is already. That's just mg. So we can substitute all this in. So we get QV over L minus mg equals 0. I want to solve for Q. Right, so once you get this set up, really the entire part of this problem is recognizing the electric force. Once you get that set up, it's pretty easy. Q equals mgl over V, right? You can also approach this problem in terms of energies, right? Energy must be conserved. And so if we say that energy is conserved, right, delta E equals 0, and it's traveling at constant speed, our energy is made up of only two parts, right? Delta UG plus delta UE equals 0, right? So this might actually be an easier approach because it's easier to connect them together. We know what the change in gravitational potential energy is, right? It's negative mgl. That's how far we fall. And the change in electric potential energy, in this case, because we're going, right, since the electric force has to sort of oppose gravity, we're going from low potential to high potential, so we have to increase our potential energy. And this lets us quickly solve for Q as well, right? mgl over V equals Q, right? Either one of those approaches works. You get the same result, right? Okay. So now we have some data. We have data points of charge, Q, versus potential difference, V. And you notice it's got that sort of 1 over x type shape, which is good, right? Because that's what shape we expect here. Q and V should be a 1 over x type shape. That matches what we found. That's actually a good way to check your answer from part A. And we're asked for a reason, a physical explanation for the gap in data points between 1700 volts and 2800 volts. And so because it's asking for a physical explanation, you can't say something like, oh, they just didn't take any data in that region. That's not a physical explanation. A physical explanation has to be something why they could not, no matter what they wanted to do, get data there. And the idea of this is really just one concept. Charge is quantized, right? I can't have a fraction of a charge. If you look at a fraction of an electron's worth of charge, rather. So if you look at the y-axis values, right, this is times 10 to the negative 19th coulombs. So 1 electron is 1.6 times 10 to the negative 19th coulombs. 2 electrons, 3.2 times 10 to the negative 19th coulombs, right? So we can't have something like 2 times 10 to the negative 19th coulombs worth of charge. And if you look at the data, right, we see a number that looks like about 1.6, that's around the 2800 volts, and then a number that's around 3-ish for the 1700 volts. You can't possibly take data in between that area because that would require you to have 1.5 electrons worth of charge. Right, so anything that talks about charge being quantized would get you the point for that. So right, that's the key. Charge is quantized. That's part B. So now, part C, just plug in some numbers. Right? We know the value of L, and we want to calculate the mass. We have to take this relationship and just kind of rearrange it a bit differently, right? So M equals QV over GL. So we need values for V and Q, right? These. We know L and we know G. And so these have to come from the graph, Q and V. Because this is not a linear graph, right? It's a 1 over x shape. You can't do a best fit line, not very effectively. So you have to just pick a data point. This is one of the rare times where you have to actually pick a single data point, not a best fit line, nothing like that. You can't do a good best fit line to a 1 over x shape, so don't try. Just pick a data point. If it's linear, best fit line. If it's not linear, data point. So pick any data point, right? Something like Q equals 1 times 10 to the negative 18th coulombs. V equals 500 volts works. We're told L is 0.050 meters, and G is 9.8 meters per second squared, right? If you plug all that in, you get M equals something like 9.8 times 10 to the negative 16th kilograms. Right? Something like that. Depending on exactly what data point you pick, you might get a slightly different number. But it should be something in that sort of region, right? The key is pick a data point and use that so that way you get your values. For parts D and E, now we're changing things up a bit. We still have that capacitor. We still have that same potential difference. But now we're adding a magnetic field in the bottom half. And so the first thing we have to do is describe the motion of the sphere. And so this is going to be a bit of kinematics in words and a little bit of like right-hand rule things, right? So saying anything, well, it's going into a magnetic field. How do particles move in magnetic fields? Circles, right? Curves. Anything that says it's not a straight line motion. So D part 1 is circle or arc or curved, something like that, to indicate the direction kind of is going to change. And then part 2 is describe, so again, not a calculate. We have to describe how knowing that motion would determine the sign of the charge. So this is where the right-hand rule comes in. Right? So if Q is positive, we know it's going to go in a circle, but which direction of the circle? Right? So V is down, V is into the page, and so it's going to make circles like where the first curve goes to the right, right? So Q positive, right? The path of the particle in the magnetic field will look something like that, right? If Q is negative, on the other hand, when it comes in, it's going to curve the other way, right? Like that. And so some description of this right here, where you say that if it's positive, it curves like this. If it's negative, it curves like that, referencing the right-hand rule. That's what you need. You don't need to do a calculation. You just need to tell me about a direction. Right? You need to make sure to describe both. And finally, part E. If you did these pictures kind of like this in D part 2, part E is pretty straightforward. So the description of the not reaching the bottom plate means that the radius of my circle, right, when we're in the magnetic field, is such that, right, as it comes in, it goes and it just barely doesn't touch. Right? So if this is the center of my circle, then R, and R must equal L over 2 at absolute most. Right? If it's anything bigger than that, then it's going to touch the bottom plate. So we do F equals MA. Right? There are 3 forces, but 2 of them cancel, right? The electric force and gravity still cancel. So the net force is the magnetic force, and the acceleration is now centripetal. Right? And we know the expression for the magnetic force. They are perpendicular, so it's just QVB. Right? So we cancel a V. And if we solve for B, right, we get B equals mv over qr. Right? And now we have to plug in the values that we know. Right? Specifically r. Right? R is actually L over 2 in this problem, so it's mv over q, L, and then times 2. Right? And so this is your final answer.